Hello and welcome back to the lectures on high performance scientific computing. So far we have been learning the intricacies of OpenMP, and today through a live example we will see how to implement and parallelize a code using OpenMP. The code that we are going to use is an existing serial code which will then be parallelized and run on a shared memory machine. First, we will try to understand a little bit about the scientific principles behind this code. The problem that we are trying to study is one of steady-state heat conduction. Now, try to imagine that there is a square plate of some material which has constant conductivity. Now, this square plate is subject to different temperatures along different edges. For example, on the top edge, it is subject to a constant temperature of T0 or maybe 0 degrees. On the left edge, it is also subject to a constant temperature of T0, which in the example we will set it to 0 degrees. On the bottom and the right edge, the temperature is varied linearly from T0 to some T infinity, and in this case, we will set that to 100 degrees. So essentially what we are saying is that on the top edge and the left edge, the temperature is held constant at 0 degrees Celsius, and on the bottom and the right edges, the temperature is being varied linearly from 0 to 100 degrees. The problem is to find out what is the temperature distribution on the internal of this square plate. One would ask, what are the governing equations that are used to model this phenomena? The governing equation that is used is called Laplace's equation, which is given in this form: del square T by del x square plus del square T by del y square is equal to 0. Now, this is assumed to be a two-dimensional problem where the variation in the third dimension is neglected. Now, as we know, we have to discretize this problem on a grid. By discretization, we mean that we will be sampling the solution at certain finite points. In this case, we are going to take uniform number of points in the x dimension and uniform number of points in the y dimension. So essentially, data now can be stored in a computer using a two-dimensional array. Each point on this two-dimensional array is denoted by two indices I and j, and you have any intermediate point denoted by these indices I and I comma j. We will have the index I incrementing along the x direction, we will have the index j incrementing along the y direction. We will also assume that these points are being sampled at uniformly spaced intervals. That is, delta x is equal to delta y is equal to some constant. So, in this case, the point I minus 1 comma j is at a distance of delta x from I comma j. The point I comma j minus 1 is at a distance of delta y in the direction of the y axis from the point I comma j. And we will have essentially an n cross n matrix to work with. So, I now have a continuous differential equation over here, which now I need to convert it into an algebraic equation. Now, typically one method is to discretize this about a single point. If you were to take a class in numerical analysis, you would readily recognize this equation. You have T of I minus 1 comma j minus T I comma j plus T I plus 1 comma j divided by delta x square plus T I j minus 1 minus T I comma j plus T I j plus 1 by delta y square, and the whole thing is equal to 0. Now, this is written for each and every pair of I comma j, and then we have to assemble all these equations for all the unknown points. Remember, if we go back to the square over here, the known values are only on the boundary because that's where we set the boundary conditions of this problem. The other thing that you will notice is that this problem is a steady state problem, which means that there is no derivative in time, which also means that there is no initial condition. There is only one steady solution to this problem. So, if I were to write a linear equation for each and every I, j point, I will have n, n such equations. I can now assemble all these equations for all the unknown internal points in the matrix form Ax is equal to b, and then I can choose to solve this problem using either an iterative technique or a direct technique. We have seen that iterative techniques are more efficient, and we have discussed them at length in previous classes. So, how do we go about implementing this in a code? So, we will now try to use one such iterative method to solve this system of Ax is equal to b, and this is called successive over relaxation. We will first see the serial implementation of this code, and then we will get some hints on how to parallelize it. We will then put in a parallel implementation, and then we will study the results of this parallel implementation. So, let me first open up the serial code. So, there is a little bit of header information about who wrote this code and when. As you can see, this is a very old code from 1994 which has been floating around. The actual code starts over here. So, now here we have defined the number of columns and number of rows as 1000. Remember, we are using an iterative method for solution. So, we have also defined the maximum number of iterations that we are going to do, which is about 1000. We have about 4 functions in this code. One is an initialize function where we have to sort of initialize all the two-dimensional arrays which are required. We then need to set the boundary conditions, which is this function. Then we actually have to do the calculation, the iterative calculation. And then for debugging and just to get an idea whether the code is doing correctly or not, we have a print function which sort of prints out the values at certain points to see how the simulation is progressing. This is where the main code starts. So, here we have the iteration counter, n-iter, and we have two-dimensional arrays, one t and one t old. Remember, when we are doing this calculation iteration by iteration, we will be at one current iteration and we will be at one previous iteration. The previous iteration is stored in the array t old and the current iteration is stored at t. The number of unknowns is 1000 by 1000, but the number of boundaries where the information is known, we need to add them. That is why the dimension of these two-dimensional arrays is nr plus 2, nc plus 2. The two additional rows and two additional columns which come in are because of the top and bottom boundaries and the left and right boundaries respectively. We have a similarly dimensioned t old matrix. We have a few counters for timing this code. So, the first function that we call is the initialize function. The second function that we call is the set boundary condition. Then, the first thing that we need to do is also initialize the second array, which is the previous temperature. The initialization and the set boundary condition is taking place to the two-dimensional array t. We then set t old or the previous iteration to be the same as t. So, at the start of the program, both the values of t old and t are essentially the same. In this case, for simplicity, we are setting the number of iterations to 1000 and we are sort of hard coding it. In reality, this is not a good way of programming, but we are doing this so that we get a consistent timing study. Typically, you have to vary the number of iterations based on certain solver tolerance. which we will not be covering in this particular code. The next part is the actual computation of the iterative method. So here we have a for loop where we start from the first iteration and we go on till about 1000 iterations. And for each iteration, we do call the calculate function, which passes the two arrays t and t old. And then periodically, and in this case, about every 100 iterations, or rather 10 times during the life of the program, because we are going to do 1000 iterations, we are going to print the trace of this two-dimensional matrix. By trace, essentially what we are meaning is that we will print the last 10 diagonal elements just to get an idea of the temperature, how it is evolving. Now, we will inspect all the functions about what they are exactly doing. The initialize function essentially goes and initializes every pair of tij to be 0. Remember, when we declare tij, the values at the memory locations could be completely uninitialized, could be anything. So we are specifically setting them to be 0. Then, in the set boundary condition function, what we are doing is, for the last row, we are going and setting a linear variation in the temperature from 0 to about 100. And we are also setting the right boundary condition to vary linearly from 0 to 100. With this, we have initialized the entire two-dimensional array correctly, with all the internal points now being at 0, the boundaries correctly being initialized with the linear variation on the right side and the bottom side, and it being 0 on the top and the left side. Now let us see how the calculate function works. For the calculate function, what is happening is that we loop over every I, j points, and for every I, j point, we are taking the average of the four neighbors, which is I plus 1j, I minus 1j, I j plus 1, I j minus 1. This essentially is a technique of successive over relaxation, where we continuously average the data from the four neighboring points. If we do this for a long enough time, we will asymptote to what is the steady state solution. So first, the latest iteration is computed for each and every I, j point based on the older t old two-dimensional array. And once this is done, the new data which has been computed is now copied into the old iteration, which is t old, so that it is ready to compute the next t. And this process keeps on going on for the total number of iterations that you have set. Now, let us quickly inspect the print trace. So, in print trace, all we are saying is that we are going to print the last 10 diagonal elements just to get an idea of how the solution is evolving. Now, let us go and run this program. Before we run this program, we need to compile this program, and in this case, I am going to use the GCC version 14 compiler. I am going to just do a serial compilation first, and I am going to put it in the output file Laplace serial. Now, if you notice, the executable Laplace serial is ready. We will now execute this serial code and we will see how much time it takes. For that, we will use the Linux command time, and then we will execute the serial code Laplace serial, and you will see that after iteration 100, this is the value, so on and so forth till you get to about 1000 iterations. And after 1000 iterations, you can see that the cornermost point is now approaching a value of 100, which is approaching the steady state solution. And you can see how the temperature varies along the diagonal. If you would like, you can visualize this in a two-dimensional plot as well, where you could see the variation of temperature in both the dimensions. What we are also seeing is that the total amount of time that this code has taken, which is about 5.19 seconds in serial. We also need to note how the code progresses, especially with regards to the solution, and we should keep certain numbers in mind. For example, I will note this last temperature, which is 99.77987671. For convenience sake, let us just try to remember these last 4 digits, 7671. And let's see, when we implement our parallel solution, do we get reproducible results? Getting the same answer, whether it is a serial code or a parallel code, is very important. And this is called code reproducibility. Scientifically, there can be only one correct answer for this problem. And if your code is going to produce different answers for different implementations of the program, then definitely we have got something wrong. Whether we have an OpenMP implementation, whether we have a distributed memory implementation, whether we have a GPU implementation or a plain serial code, we should always get the same answer for the same problem. So first, let us begin to implement the parallel version of this code. So let's start with the same code, Laplace C, and I will start putting in pragmas from what we have learned. So I will now first include the OpenMP header to get the OpenMP functions. So I'll have to include this. Then when I go here, I would like to now time how much time it takes to do this entire calculation over here. The initial part of the code is just some sort of a setup time. So we will now say start, which is counter, is equal to OMP get W time. I hope I have my syntax correct. Now, this is the entire code over here, and now this is where the program finishes. So I will say end is equal to OMP get W time. This is the function which gets the clock time. And finally, I'll say printf the time taken is. I'll put it in a certain format and have a new line, and I'll say it is end minus start. Now let us see if we are able to compile this program. So I have to say GCC. In this case, I do have to say the flag f OpenMP because I'm calling some OpenMP functions. Laplace.c, and this time I'll say Laplace OMP as the executable. And you can see how the compilation has taken place. Now let us execute this file Laplace OMP. Remember, we have really not done any parallelization to the calculation. The only thing that we have added is a timing function. So we are running this code and we see the time now that is taken is 4.8375 seconds, and we are getting the same reproducible answer by just noting that the last 4 digits of the corner point is 7671. Let us run this code once more to see is there any variation in the time taken. There is a slight variation from the 3rd decimal onwards. So you notice that there will always be some amount of time variation which is done because the operating system, when it schedules the code onto the processing cores, it is doing some other tasks as well. So there could be some minor variations in the time. Hence, it is always a good idea while reporting times in a timing study to take an average of few runs. I strongly recommend taking an average of about 5 runs. But now let us keep this time in mind, where for the serial code, where we have not done any parallelization, the time that is taken is about 4.83 seconds. Now let us go and parallelize the code. So if you look at it, in this code, the bulk of the work is being done in the calculate function, where for each and every point, you have to go and compute the new t. So that should be the primary target of our parallelization. So let's see how we can parallelize the code. So you see, this is where most of the code is being taken place. So one of the easiest ways we said is to use a OMP for. So I can say hash pragma OMP for, and this will implicitly parallelize the next loop. So I have this loop which has been parallelized, and I can do the same thing for the copy as well. I say hash pragma OMP. I think I have to do a parallel for. I have to do this. I'll put a parallel, and this should parallelize both the for loops. Now let us see what happens. I will now compile the code again using the OpenMP flag. With the output to be Laplace OMP in this case. And remember, I have not set the number of threads. So let me set the number of threads to be 4. So I use the environment variable OMP num threads. I set it to 4 explicitly. And then now I execute the code. The reason why I set the number of threads to be 4 is that this laptop that I'm working on is a quad-core machine. Now, let us execute this code. You see, we have now completed the execution of this code. The time that it took is about 2 seconds, which is much lower than the 4.8 seconds but we are using 4 computing cores. But another thing that you would notice is that we have a slightly different solution. Instead of getting 7671 as the last 4 digits, now we are getting something as 5100. Let us execute this code one more time to see if we are getting code reproducibility. This time we are getting a completely different answer, 5200. The time taken is roughly about the same. If I execute it a third time, we have a completely different answer here where it's about like 89, the temperature. And we instinctively know that there's something wrong going on with the program because it's not giving the same answer when we have run the code 3 different times. So the parallel code with the same parameters, same input parameters is giving different answers for different runs, and that is problematic. And it is also not matching with the serial code answers. So let us go back to the code and see where we could have gone wrong. I will quickly skip to the calculate function because that's where we have introduced the parallelization. That is over here. So the thing we are going wrong with over here is the index. We declared the indices I and j up here, so this is not an implicitly private variable. We need to explicitly say that both the indices I and j are private for each and every one of these loops. So we have to mention that in a data clause, and it is to be mentioned here. We say private and I comma j over here, which means that for every parallel thread, the index I and j will now be separate and each one of it will have its own individual copy. And this is important to maintain the coherence of this program. Now let us go back and compile this program. I compile this code again, giving it the same executable output. And in this case, I will now run the code again. Now you can see that we have the exact same answer, 7671, and we are also much faster. The reason is because now each thread has its own copy of I comma j. That means the code is consistent. It is not making any mistakes by rewriting and overwriting I comma j. There is no issues of data races between those indices, and we are getting the same correct answer. We can now vary the number of threads on this machine to see what will be the effect on timing. So now let us see how we can change the number of threads. We are going to now vary it from say 1 threads. I set the variable to be OMP num threads to be 1. This is essentially a serial code, and we'll see how much time does this code take. We will get the same answer every single time. See, we get 3.22 seconds, the total runtime of this code. You must be wondering why is it so much lower compared to when we ran the plain serial code and used the Linux time function. That was because this timing is done only inside the code and is not taking into the overheads of loading the entire serial program. Now I will change the number of threads to 2, and let's see how much time we get. So if we take about 3.22 seconds for 1 thread, with 2 threads we are taking about 1.7 seconds, which is a little bit more than half. So we are getting a speed up less than 2, which is to be expected in these cases. Now if I change this to 4, we will see that we get about 1.05 seconds. So we are getting a speed up of just over 3 when we are using 4 processors. Let's see what happens if we use 8, because remember we can schedule more threads than the available number of cores. And in this case, we get some marginal improvement in our speeds. In the next class, we will see the effect of ordering these different pragmas and how it affects the placement and the runtime. Thank you.